Here's the question that I want to address right now. What's the derivative of some constant multiple of some function? Now, in this case, the constant multiple is 2, but of course that 2 could be replaced by any fixed number. If you don't like the ddx notation, another way to ask this question is this. If you've got some new function g and it's this constant multiple times f, again in this case I'm using 2 as the constant, the question is what's the derivative of g in terms of the derivative of f? To gain some intuition, let's pick a specific example and look at a graph. So here's the graph of just some random function. Let's suppose that I stretch this graph in the y direction. So now I stretch the y-axis, and that corresponds to multiplying the function by a constant value, in this case 2. How do the tangent lines change when I do this stretching? So if I double the y-axis, the function changes by twice as much for the same input change. So if I double the y-axis, the slope of the tangent line also doubles. And that makes sense numerically. Here's what I know. I know that g of x is twice f of x. G is that constant multiple of f. I also know something about the derivative of f. The derivative encodes how input changes become output changes. Or a bit more precisely, the derivative in the limit is the ratio of output change to input change. So if I multiply the ratio of output change to input change by an actual input change, this, at least approximately, is telling me how much the output should change when I move from x to x plus h. Right? F's new output at the input x plus h is its old output plus how much I expect the output to change. This is a really nice way to summarize what the derivative is saying. Now, I know one other thing. I know that g of x plus h is twice f of x plus h just because g is twice f for any input value x. So in particular, that's true when the input is x plus h. Now, these two statements are connected. Right? G of x plus h is twice f of x plus h, and f of x plus h is approximately this. So I can combine those two statements together in this statement. G of x plus h is about twice f of x plus h's approximate value, right? Twice f of x plus twice h times f prime of x, which I've written as h times twice f prime of x. I can make this a little bit nicer. Since twice f of x is g of x, I can replace this 2 times f of x with g of x. And this is really looking good. This is telling me that g's output at x plus h is about g's output at x plus how much I change the input by times some quantity. Now, considering that the actual derivative of g would tell me some information like this, that g's output is about g's old output plus how much I change the input by times the derivative, you're beginning to see what's going on here, right? Look, I've got the derivative of g here, and I've got twice the derivative of f here. And if you sort of believe that these statements are connected in this way, you might then believe that the derivative of g is twice the derivative of f. The derivative of g here is twice the derivative of f. We can formalize this as a rule. Here's the constant multiple rule. So let k be a constant, and suppose that f is just some function which is differentiable at the point a. G is that constant multiple of f. So g of x is k times f of x. Given this setup, what the constant multiple rule is concluding is that the derivatives are related in the same way. The derivative at the point a is k times the derivative of f at the point a. Now, if you don't like this prime notation, you could also write it using the ddx notation. So here's how I write the constant multiple law using the ddx notation. The derivative of k times a function is k times the derivative of that function. I encourage you to keep practicing. With time, you'll be able to calculate the derivative of just a ton of different functions.